Today I will talk about system dynamic modeling, which is part of my series of lectures on simulation, and it is under business analytics. So this is my lecture outline. First I will give introduction, then I will talk about structure of system dynamic model, then I'll talk about steps of system dynamic modeling, then I will give you an example, and also with another example I will describe Python code for system dynamic modeling. So this is a simple model in terms of system dynamic modeling. So there is a inflow birth, there is a outflow death, and there is a population. And the inflow depends on birth rate and number of people which are existing. And death depends on the lifespan and the number of peoples which are there in the system. So this is a simplest system dynamic model of population. System dynamics is a computer-based mathematical modeling approach for strategy development and better decision making in complex systems. The main goal is to help people make better decisions when confronted with complex dynamic systems. It can be applied to social, managerial, economic, ecological, and physiological systems. It uses simulation modeling based on feedback systems theory that complements systems thinking approach. Diagram of the primary feedback loop in the system are often converted into computer simulations to model how changes in one part of the system may affect other and the overall pattern for development. So there are two approaches. One is system thinking approach. System thinking is a causality driven approach to describe the interactive relationship between components, and system dynamics complements system thinking by quantifying interactions and develop a time dependent view of how the system behaves. And this is a holistic approach. The structure of system dynamic model. It has stock, that is population in our example. It has flow, that is inflow and outflow. It has converters and connectors, and it has feedback loops. Then principles behind system dynamic model include dynamic thinking, that is, there are changes over time, causal thinking, that is feedback loops, stock and flow thinking, that is accumulation, population in our example, and thinking endogenously, that is system as a cause. Then variables in system dynamic model may be internal to the model or external from the model. Internal to the model, they affect the system and are affected by the system. External variables, they affect the system but are not affected by the system because they are external to the system. Then system structure include resources and accumulations, causal structure, that is feedback loops, policies, example government policies, government decisions, affect and emotions, then rationalities and irrationalities, pressures, perceptions, and delays. Now let us see steps in system dynamic modeling. First of all, we identify the objective for the simulation. Then we draw a schematic diagram with labeling process variables. Then we list all assumptions. Then we determine spatial dependence. Then we write dynamic balances, that is mass, species, energy. Then we define other relations and we do the simulation. Example, this is the simplest model. As we have seen, it has an inflow and outflow and accumulation as in the form of population here. And so it has a stock of people, that is population, inflow of birth, outflow due to deaths. And we can add net flow from migration, migration in and migration out. And the parameters which are used include birth rate, life expectancy. So this is birth rate, this is life expectancy, and fraction of people migrating out. So these are the parameters which are used in a simple population model. So now let us see an example in Python code of system dynamic model. So there are these basic, one is NumPy and the other is for graphical output. So we import these two libraries. Then we initialize the variables. So the simulation length we set as 48, and the birth rate is 0.1. This and death rate is 0.1. So both the rates are same, and the steps of time we take as 0.01, and number of iterations include the calculation as simulation length divided by the time intervals, and the population is this is the array, and then we set the initial population as 100. So then we start the simulation, and this is the mathematical formula. So the growth is equal to growth rate multiplied by the population present at time I. So it depends on growth rate as well as population. And death is equal to death rate multiplied by population at time I. So it depends on death rate as well as the population in a particular time. And the population is equal to population plus growth and minus death. So we start the simulation, and after simulation, we got a straight line because the death rate and birth rate, they were same. So population is 100. It started with 100, it will remain as 100. Now let us change the parameters, because we can experiment in simulation and we can see the effect of changing the input variables. So the simulation length is same. Growth rate, we have doubled the growth rate, and death rate remains same as previous example as 0.1. Time intervals 0.01. These are number of iterations, and this is the population array, and the initial population is 100. So when we this is the mathematical equation, and when we run the simulation, we get an exponential curve. So this is all for today. Thank you.